So far we've seen that moving electric charges can create magnetic fields. And from Ørsted's experiment, we've seen that these magnetic fields can interact with permanent magnets. So these fields can exert magnetic forces on things. So it has to be the case that in order to satisfy Newton's third law, that somehow magnetic fields have to be able to exert forces on moving electric charges. And that turns out to be the case. The magnetic force that is exerted on some charged particle that is moving through a magnetic field is given by QV cross B, where B is the, where we're talking here about the cross product. So B is the magnetic field, V is the velocity of the particle, Q is its electric charge, and the force that it feels here is the magnetic force. So again, we've got cross products involved here. So this means that the magnitude of the force will be equal to QVB sine phi, where phi is the angle between the velocity and the magnetic field vector. So let's just say here we have a magnetic field that is going into the screen. So when I'm drawing a bunch of X's here, you should be thinking about magnetic field lines perpendicular to the screen and pointing into the screen. So let's say we have a positive charge that is moving to the right. Like so. Which way is this charge going to be feeling a magnetic force? Go ahead, take the cross product now, and then we'll compare. So hopefully you got that the magnetic force is, at this exact moment, is going to be pointing up on it. Now, when we repeat this for a negative charge, so let's say we have a negative charge that is moving to the right. Now here it's a matter of taste. When you're doing your right-hand rule, what I usually like to do is I multiply the charge against the velocity right away. So I'll be pointing my first finger to the left. And so go ahead, take the cross product, see what you get. All right, so hopefully we are in agreement here that the magnetic force points down. Now I do have some tricks for helping to keep this all straight when applied to magnetism, which I'm going to get into right now. When doing cross products to find magnetic forces on moving charges, I like to modify how I do my right-hand rules just a little bit. So what you're seeing right here is I've actually made a little widget out of Tinker Toys, and you can do this with Tinker Toys or with pencils that are taped together, anything like that. Just make sure that you have it oriented exactly like this. You have charge times velocity here. You have magnetic field 90 degrees counterclockwise away. And then you have the force pointing perpendicular to the plane, like that, and in the sense of the right-hand rule. So here's how I like to do right-hand rules when magnetic fields are in play. Normally I just do 3 fingers, but here now I will put all 3 fingers out here. And this is a bit of a mnemonic to help me remember that this is the magnetic field, because this looks like magnetic field lines. So what I'll do is I will put the charge times the velocity here. So if I have, say, a proton that is moving to the left, then I would point my index finger to the left. However, if I have an electron that's moving to the left, I would have to point my index finger to the right. And then the same idea from there. You rotate your hand around your index finger to match the magnetic field fingers, and you can go ahead and move these back and forth, and the force will be on your thumb. Now, when you're doing this with current segments, you realize that if you have a positive charge times the velocity, that will always point in the direction of conventional current. Or if you have a negative charge times its velocity, that would also point in the direction of its conventional current. So I put the index finger along conventional current, rotate my hand around it to match the field fingers. Force is on the thumb. This gives a bit of a mnemonic also for remembering which finger goes with which item. Is you can remember to always tell a fib, F-I-B, because the force is on your thumb. The current, I, is on your index finger, so I goes to I there. And then the magnetic field fingers are these here, matching the magnetic field. All right. So if you take a look at these forces here as we're moving through the magnetic field, in this example here, I have the velocity vector absolutely perpendicular to the magnetic field. So if that's the case, what sort of trajectory would we be taking on for our charges here? Go ahead, pause the video, and get back with me on that. Yeah, it's going to work out that our trajectories are going to be circles. In this case, where V is perpendicular to B. And the reason for this is that the force is always perpendicular to the motion. So that means that all that force can do is change the direction. It can't change the speed. So we can go ahead and figure out what these forces are. Let's go ahead and just to make this concrete, let's assume that our positive charged particle here is a proton, and our negatively charged particle here is an electron. Let's go ahead and say that in both cases, the particle was moving at 1,000,000 meters per second. And let's say the magnetic field strength was 1/10 of a Tesla. I'd like to figure out for both the proton and the electron, what is the magnetic force and what is the acceleration of the particle. Well, let's start with the magnetic force. So we've already got the directions worked out by the right-hand rule, so we just need to get the magnitude here. So the magnetic force is going to be equal to QVB times the sine of the angle between V and B. Now, here, B is going straight into the screen, and V is going straight to the right on the surface of the screen. So that's a 90-degree angle. And that's true regardless of whether it's the proton case or the electron case. V and B are making a 90-degree angle. So this will be equal to QVB sine of 90 degrees, and the sine of 90 is 1. The charge in both cases is going to be the fundamental quantum of charge E. The only difference that the sign is going to do is change whether it curves up or it curves down. So we can go ahead and substitute our values in here. So the fundamental quantum of charge is 1.6 times 10 to the negative 19 coulombs. We decided that the particles were moving at 1,000,000 meters per second in a 1/10 of a Tesla magnetic field. So both particles are feeling a force of 1.6 times 10 to the negative 14 newtons. Now that might not seem like a very big force, but keep in mind these particles are pretty lightweight, and so the accelerations will actually be pretty substantial. Let's go ahead and figure that out. So the acceleration will be equal to the force over the mass by Newton's second law. And we just worked out that the force was 1.6 times 10 to the negative 14 newtons. So now let's go ahead and do the proton here. So for the proton, the mass of a proton is 1.67 times 10 to the negative 27 kilograms. So we get an acceleration of 9.57 times 10 to the 12 meters per second squared. Okay, now let's go ahead and do this for the electron. So in case of the electron, the mass of an electron is 9.11 times 10 to the negative 31 kilograms. The electron mass is actually, there is a nifty little mnemonic to sort of remember it. You can remember the first three digits by just remembering to call 911. So 9.11, and then I use the fact that 10 to the negative 31 rhymes with 911. So 9.11 times 10 to the negative 31 kilograms, we get an acceleration of 1.76 times 10 to the 16 meters per second squared. Now, it's always good to do a sanity check on these things. And it's always a good idea to make sure, for instance, that things aren't violating relativity. So here we've got that the proton is doing 9.57 times 10 to the 12. The electron's doing 1.76 times 10 to the 16. But the speed of light is 3 times 10 to the 8, and we can't be going faster than the speed of light. So did this turn out to be a physically unrealistic example? Pause the video and get back with me. All right, it did not turn out to be a physically unrealistic example because we're comparing apples and oranges. Notice I was being a little sloppy about units there. These are accelerations. They're in meters per second squared. When you're comparing, you can't compare it against a speed, which is in meters per second. You can only compare quantities that have comparable units. Here, they don't, so a comparison like that is meaningless. So these are perfectly good, albeit extraordinarily large accelerations. So even though it's a small force, these are very lightweight objects, and so they get whipped around pretty hard. Okay, so we've already worked out that the motion of a charged particle in a magnetic field where V and B is perpendicular is a circular path. So I'd like you to go ahead and take a look at this video here. So what you are looking at here is a demonstration apparatus to show the trajectory of electrons moving in a magnetic field. These copper coils that you see here are called Helmholtz coils. They're a special configuration of coils where the magnetic field inside the coils is very nearly uniform. Now the current going through the coils will be going around like this, counterclockwise as you see it. If we follow that along with our thumb, we can see that the fingers of our right hand curl around the coil. So that means that the magnetic field from the coils will be pointing out of the screen at you. This tube here is mostly evacuated, except that it has a small amount of mercury gas in it. And this little metal mushroom cap looking thing over here is an electron gun. Electrons will be fired downward by the electron gun, and we can figure out which way they'll be feeling a magnetic force. So I have here a nice little right-hand rule widget. So we'll align the magnetic field to match the magnetic field of the Helmholtz coils. Now the electrons will be fired down. However, since electrons are negatively charged, we'll put Q times V up. So that means that the force will be pointed at right angles to the motion inward. So we expect that it'll be going around in a circle. In fact, there's a little grounding plate right here for them to land onto. Now, the way you'll be able to see the motion of the electrons is that every so often, one of the electrons in the beam will strike an atom of mercury in the mercury gas that's in the tube. When that happens, it'll excite the mercury atom, and when it de-excites, it will emit sort of a purplish light. And so we'll be able to see a trail left behind by the electrons as they travel through the mercury gas. Now, in order for us to see this, we're going to first have to button up the apparatus, and then we're going to have to turn out the lights in the room so that we can see what's going on. Okay, so we can see that, sure enough, the electron beam is indeed taking a circular path. So you might ask yourself, what would happen if I increase the accelerating voltage in the electron gun? Go ahead and pause the video, make your prediction, and then we'll check. All right, here we go. Oh, well, you know, the radius is getting bigger. Okay. And now, you might ask yourself, what will happen if I increase the current going through the Helmholtz coils? So go ahead, pause the video, make your prediction. Well, you know, the radius got smaller. All right, so let's think about the radius bit first. So we worked out already that for our charged particles, they will always be moving around in a circle. In the video that you just saw, that circle, we were looking at electrons. Just to simplify the discussion a bit, we'll think about positive charged particles moving through the field, but you get the exact same answer. It's just that the electrons move around in the opposite direction. All right, so we'll go ahead and imagine a positively charged particle here. Again, it's moving to the right, and you should be doing the right-hand rule on this to be convincing yourself that the magnetic force is always perpendicular to it, like that. And here, where we have that V and B are perpendicular, that we saw that the motion that we are going to have is a circle. So just a real quick question to ask yourself here is, can we come up with an expression for how much work the magnetic force did as our particle moved around this one complete orbit of the circle. Go ahead, pause the video, and get back with me. All right, so hopefully we agree that it did no work. The force was always perpendicular to the motion, and we can only do work if we have a component that's either parallel or anti-parallel to the motion. So we expect that the speed of the particle should never change. So in this case here, because we're going around in a circle, we can recognize that, we can just say F net equals ma. And if we go ahead and just take a look at the radial component of this, we can say, oh, the net force here is just the magnetic force because it's the only force we've got. And this will have to be equal to m. And our acceleration here will be directed towards the center of the circle. That means that it is a centripetal acceleration, which we remember is equal to v squared over r. So we can put in what the magnetic force is here. This will be QVB, and it'll be equal to QVB times the sine of the angle between V and B. But B is again straight into the page in this example here, and the velocity is in straight into the screen, and the velocity is on the surface of the screen. Again, that is a 90-degree angle. So we can go ahead and substitute that our angle phi here is 90 degrees, which makes that sine function equal to 1. And that's going to be equal to mv squared over r, where r is the radius of our circle. All right, so we can even solve for r. We can cancel 1 power of v there. And we get that r is equal to mv over qb. So this radius has a interesting historical name. It's called the cyclotron radius. A cyclotron is a special kind of particle accelerator so that you don't have to build a very, very long accelerator. People came on the trick of, hey, if we stick the whole thing in a magnetic field, we can force the charges to be going around in circles. And at 2 points on the circle, they would create an accelerating electric potential. And so the idea is, okay, well, how big of an orbit are you going to have? And this is how big of an orbit you're going to have for your cyclotron. So this gives you some guidance on how to build the cyclotron. Now, in practice, the speeds these particles get to wind up being substantial fractions of the speed of light, and this equation has to be modified. But if things are going a smaller percentage of the speed of light, this works just fine. All right, so looking at that gives us maybe a little bit of a clue on why increasing the current through the coil caused the radius of the particle to get smaller. Because if we increase the current in the coil, we made the magnetic field bigger, and a bigger number in the denominator means we're going to have a smaller number in the top, because what we did was, by making the field stronger, we made the magnetic force bigger. Likewise, when we increased the accelerating voltage, that made the particle itself go faster, and so since it's going faster, that required it go around in a bigger circle for the same centripetal force due to the magnetic force. Now, an application of this is mass spectrometry. A lot of times, this relation can be rewritten just purely around the kinetic energy of the particle. And what will pop out is a charge to mass ratio, is a mass to charge ratio of the particles. So say if you're doing something like radioactive carbon dating, what you need to know is the ratio of carbon-12 to carbon-14 nuclei. These differ in that the carbon-14 has 2 more neutrons than carbon-12, so it makes it a little more massive. And we can see here, for the same speed, if we're a little more massive, you'd be going at a bigger radius. And so this is the sort of principle that gets used to figure these percentages out. You accelerate things to a known kinetic energy. You measure the radius of curvature that the particles take by measure the radius of curvature the particles take, and from that you can deduce the ratio of the mass to the charge of the particle. In order for this to work, you have to ionize the particles. So a lot of times this charge is just 1 because it's a single ion. All right, so we took a look at the case of the velocity and the magnetic field being perpendicular. What kind of a trajectory would you have if the velocity and the magnetic field are parallel or anti-parallel? So I'm including in here both the possibility that they are directed in the same direction or exactly 180 degrees apart. What kind of motion do you have in that case? Go ahead, pause the video, and get back with me. All right, well, it turns out in this case, the motion just keeps on trucking. So let's say we've got our magnetic field pointing to the right, and again, just for simplicity's sake, let's think about a positively charged particle. Let's say it's moving again straight to the right. Well, the magnitude of the electric force, remember here, is QVB sine phi. So this will be QVB, and for this example, be sine 0, but the sine of 0 is 0, so the force is 0. You say, well, that's great, but what if instead of it moving to the right, you had it moving anti-parallel to the field to the left? Well, in that case, what you would have is QVB sine of 180 degrees, because our angle phi between the magnetic field pointing straight right and the velocity pointing straight left is 180 degrees. So the sine of 180 degrees is also 0. So again, there is no magnetic force either way. So the particle just moves on undeflected. All right, well, what about then the more general case? What if our particle is moving neither parallel nor perpendicular to the magnetic field, but just at some random angle? So we'll say that the angle between V and B is equal to something something as long as it isn't 0, 90, or 180 degrees. What does the motion look like then? What do you think? Okay, so in this case, the motion is what's called a helix. which is just a fancy name for a corkscrew kind of motion. So again, let's imagine that we have a uniform magnetic field pointing to the right, and I'm really sorry for how badly I'm going to be attempting to draw in 3D. So let's say we've got a positively charged particle, and it's doing some number like this. Well, we can break this motion up into two bits. We'll have a parallel bit and a perpendicular bit. This bit never changes. This bit here will be constantly changing direction. And so probably the easiest way to think about this would be to imagine if you were moving to the right at v parallel, you would just see the particle moving around in a circle in this plane here. But then to some observer who would be seeing you moving to the right, you'd have to superimpose that motion on top of it. So the trajectory you'll get will be a circle that's been kind of spiraled out, so you get sort of a slinky or a corkscrew kind of action going on here. Now, this sort of a thing is of actually great interest. And there's a really awesome application of this. It's a phenomenon called the Aurora. So, depending whether you're in the northern or the southern hemisphere, you'll call these the northern lights or the southern lights. So, if you live far enough north, depending on where you are in the sunspot cycle, because it turns out the charged particles coming off the sun have something to do with the exact shape of the Earth's magnetic field. What you wind up having happen is, let's say we have the Earth here, and I'm going to try to draw a better Earth than I have before, and well, I tried. So let's say you have the Earth here. Way out over here, we have the sun. And what you have coming off of the sun is lots and lots of charged particles. The fancy name for this is the solar wind. Now, the Earth has a magnetic field, and because of interactions with the magnetic field, the shape of it gets deformed somewhat. So in front it tends to get squished up, and in back it gets kind of stretched out to look something like this. This point here gets called the reconnection point. And so what will happen is, due to interactions with the Earth's magnetic field, a lot of these charged particles will just plain go around the Earth like so, just like streamlines of water around a ship, or air around a aircraft. In fact, you'll even get a region right here where the particles tend to pile up, just like the water does at the bow of a boat, and it gets called the bow shock. However, this isn't perfect. So what will happen is that some of the particles will manage to be moving at just the right speed and in just the right directions. What will happen is they will start to interact with the local magnetic field. Now, likely what will end up happening is the particles will get deposited in one of the two Van Allen belts that hang out here and here. I'm not going to draw them in for clarity. But some of them, especially the ones coming in the polar region, will actually wind up wrapping around, if you will, the magnetic field line and corkscrewing along, doing this corkscrew motion that we just saw. Now, it's a treatment beyond the scope of what we're doing here, but because the magnetic field strength is changing, because the density field lines is increasing here, regardless of whether the particle is positively or negatively charged, there will be a magnetic force that will be first slowing it down and then making it reverse direction along the magnetic field line. So then what will happen is it'll corkscrew its way along the magnetic field line, get to the other end, then corkscrew back and forth along the magnetic field lines. Now, if these particles are energetic enough, they strike the upper part of the Earth's atmosphere. And when they do, they excite the air molecules in the atmosphere. And by kicking the electrons in the molecule up to a higher orbit, when those electrons return to a lower orbit, they emit light of the pretty colors that you see when you see the northern or the southern lights. Alrighty. In the next video, we will take a look at an application called the Hall effect, which is what we use to determine the sign of mobile charge carriers in a material. Catch you over there.